Okay, students, we are going to now start on the rest of chapter 15, but it's going to be either a long lecture or I might have to split it up into two simply because there may not be enough memory on my computer to do the rest of the chapter straight through. So we'll have to see this because this would go from a whole bunch of slides, at least 200. So more than likely it'll be two lectures. But the material is not all that difficult actually. It's much easier in chapter 13 and 14, and partly because it's Green's functions, which some of you should have had experience with Green functions before. So it's not totally unusual material. So this is starting on sections 15.4, I believe. Let me see here. Yeah, I'm pretty sure it's 15.4. It's two-dimensional Green's functions, which is 15.4. All right. So we're going to be looking at two-dimensional Green's functions, first in rectangular coordinates. Later on, we'll be looking at cylindrical and spherical coordinates as well. But actually, we're going to be doing an example fairly soon where we do indeed work with cylindrical coordinates. So, but first, rectangular coordinates. Example one, we'll introduce this concept, meaning applying Green's functions to 2D problems or second-order differential equations. I mean two-dimensional, meaning things vary both in x and y. We're going to be looking at static electromagnetics first. Unless it's not working. So let me, this should, there we go. Okay, so two-dimensional Green's functions, rectangular coordinates. We're going to be looking at static fields. When we're dealing with statics, even when we're not dealing with statics, so we have the del squared V is equal to minus Q over epsilon naught, where Q is the charge density, V is the potential, and so forth. So we're going to be looking at, so we can, we're going to impose upon V four boundary conditions. And this could be potentially where within a rectangular cavity or a waveguide that in which we are holding the walls at zero potential. All right. So we have walls at x is equal to 0 and x is equal to a, in between y0 and yb, and also at y is equal to 0, y is equal to b, in the range of x going from 0 to a. All right. So typical thing that you would study in electrostatics. All right, so how do you apply Green's functions to this? Okay, so you take that original differential equation, this right here, 1571, and to the right-hand side, you have it equal to the product of two delta Dirac terms, one for the x, one for the y. All right. And the Green's function has to satisfy the same boundary conditions as the original problem. And when that's the case, then the potential for any x and any y will then be given by this. We've seen that in the prior lecture. All right, but we'll always have this type of thing. That's what the Green's function is all about. So once you derive the Green's function, that remains unchanged, and you can put in any charge distribution you want in here and get the resulting potential. That's the power of Green's functions. So now, okay, so the next step that you do is you will need to look at the homogeneous equation and find the eigenvalues and eigenvectors for this. Okay, so we're going to do this in a couple of ways. We're going to look at the situation and figure out the closed form solution for the Green's function, but also mix in a bit of the series form as well. All right. So skipping ahead just a little bit to something that's more reminiscent of series form, where you're finding eigenvectors and eigenvalues. This is what we have. Typically, you would solve this using separation of variables. You will have done this in your electrostatics problem. When you substitute this into this, you can separate out the dependencies. Like this, find the solution for f, and then do the same for the y dependence, and find the solution for y, and so forth. And then you would apply boundary conditions and be able to get the answer. All right. Let's do this, however, using Green's functions. First in the closed form, then in the series form. All right. So in the closed form, we start with Green's functions. For the closed form solution can be formulated by initially choosing functions that satisfy the boundary conditions either along the x direction or along the y direction. All right. So let's satisfy the boundary conditions, say in the x direction first, which means that g has to be 0 at x is equal to 0 and x is equal to a. All right. And so we're going to start with that. So let us begin the development of the Green's function, equation 1572, by choosing first the functions that satisfy the boundary conditions along the x direction. This is accomplished by initially representing the Green's function by a normalized single function Fourier series of sine functions that satisfy the boundary conditions at x equal to 0 and x equal to a. So this is what we have right here. But to this, any integer m will satisfy the boundary condition. So we don't prefer one sine function over another with different n values. We keep them all and have these as of yet undetermined coefficients in front of those sine functions. All right? And so this is how we initially express g. So this may be a little bit confusing to some of you, saying, well, aren't we solving this in the closed, using the closed form? But yet now we're introducing a series, g as a series. And the answer is yes for both. We are indeed, right now, at the very beginning, saying g is going to be a linear combination of these sine functions, a series. But now, once we're done with that, we're going to go fully to the closed form recipe for solving for Green's function. All right? So just bear with me for a second. So these GMs of the Fourier series will be determined by first substituting 1574, this right here, into the equation for g. And so we put that in for g, and then this is what we get this right here initially. We're going to multiply both sides by sine n pi over a over x and integrate over 0 to a, noting the orthonormal nature of these sine functions. And so we can select out a single value in this summation here through this process. And we are left with this equation right here, that equation right there. All right. So this is another equation. So this is the equation that that we have to deal with. All right. So this is really sort of like another Green's functions with this delta Dirac function on the right-hand side. Okay. So in the closed form solution, in the closed form recipe for finding the Green's functions, you take that right-hand side and set it equal to 0, and then find solutions for g that satisfy the boundary conditions at y is equal to 0, and then the second solution that satisfies the boundary conditions at y is equal to b. All right. Well, okay, so you have a minus here instead of a plus, so that's important. And what that means, this is just a second order differential equation of a very simple form, but you have the minus there, and so instead of signs, you're going to have hyperbolic signs and hyperbolic cosines. Okay, but only the hyperbolic sign satisfies the boundary condition that y is equal to 0. Hyperbolic sign of 0 is 0. Hyperbolic cosine of 0 is not 0. And same for y2. This has to be equal to 0. Y is equal to b. So this is the solution we choose for that one. All right. So we have y1 and y2. We have our two y's for this. And the hyperbolic functions were chosen as solutions instead of the real exponentials because they satisfy the boundary conditions. We already said that. So now we have to find the Wronskian of these two solutions at y is equal to y prime. That's easy to do. And so we do that. And so we find the Wronskian as this, just taking a couple of derivatives. It's very easy. And so we can express those Wronskians in different ways. So the Wronskian using some formulas from trigonometric, this right here, we're able to express that Wronskian like this. That's very easy. And so we have that. Now, and so we need then to cast this equation now, this equation here, into the Strom-Liouville form so that we can get P, Q, and R and F to put into our recipe. So we need P, Q, R, and F to put in our recipe of finding the Green's functions. So we said how to do that in last week's lecture, and so we can determine quite easily that P is equal to 1, Q is equal to 0, R is equal to 1, our lambda is equal to this right here, and our F is, we have an F is this right here, okay? So we have everything we need to put in and for our Green's functions for the two different regions. Right. So we can go ahead and do that to get the Green's function, to get G. So we get G, and then those G's then go into here. Lowercase g's go into here to give us the full Green's function, capital G. All right. So you might say, well, okay, well, we did it first by writing our initial series as satisfying the boundary conditions for x at x is equal to 0 and x is equal to a, but couldn't we have also done it first satisfying the boundary conditions of y is equal to 0 and y is equal to b? And well, shouldn't you get the exact same thing? The answer is yes, you will. You will get the exact same thing. It will look somewhat different, of course, because in the hyperbolic signs, you will have x in there. And in the signs, you will have y and y primes. But it produces the exact same result when you actually evaluate these equations. So. All right, so this is why I say we do things in rectangular coordinates, but we switch and do an example in cylindrical coordinates at the moment, just at the moment as an example. So cylindrical coordinates, we're looking at static fields. We're going to have the electric charge is uniformly distributed along the infinitely long conducting wire positioned at rho is equal to rho prime, phi is equal to phi prime, and circumscribed by a grounded electric conducting circular cylinder of radius a and infinite length. Find the series form of the Green's function and potential distribution. Otherwise, assume free space in the cylinder. All right. So this is what we have for our problem. And so we're going to have infinitely long conducting wire positioned here at these these coordinates. Okay, but these coordinates will be able to be anything as long as they are inside the cylinder. It doesn't matter. All right. So this is the geometry we're working with. We have a grounded cylinder. All right. And that infinite wire can have any charge distribution you want. Okay. So and we're going to find a Green's function that doesn't depend at all on Q, but it allows for you to use any Q with this Green's function to find the potential for any situation being any wire with any charge distribution you impart on it, that you have on it. Okay, but we have the boundary condition at the walls of the cylinder being that V is always 0, and so this is what we have. So this is a 2D problem at this point. So we are going to say here that for this particular example, that we do not have any charge variation in the z direction. All right, that's important for this. I'm not certain if they say that in the problem. So, but it doesn't really matter actually. So, so we can solve this whole thing if z is equal to 0. All right, that's fine. So, so we still have this boundary condition, obviously, at any z, but also certainly at z is equal to 0. Yeah, and it does matter because right here our del squared does not have a d squared over dz squared component on this side. So we are assuming that v does not have a z dependence. So therefore our g's will also not have a z dependence. Okay, so anyways, with that being said, this is the equation that we have to solve for v. So we find the Green's function for this, and for that, on the right-hand side, we change it to the delta Dirac, as we've always done. This is what we have. For g, the differential equation must be satisfied, and this is the boundary condition. All right, so series form. So, series form. We need to find a complete set of orthonormal functions. Psi for Poisson's equations can be obtained using this. So we have the homogeneous solution, and we're going to have, in this case, so these are my eigenvalues of the homogeneous solution. Okay? So this is going to go over to the other side. My r is going to be equal to 1, and my lambda is, in the Green's function, is 0, but for the homogeneous solution, it's going to be some lambda m sub n that we have right here. All right? Okay. Because first you have to put this in the Strom-Liouville situation. And we'll get back to that in a moment. So, still have the boundary conditions. We can still use separation of variables, okay? And so this is going to be important because we don't quite know what to do with this at the moment. So separation of variables, we're going to be doing that. And we will show that the G dependence here, let me write on this, G of phi has to be equal to something of the form G and phi, like that. Take two derivatives of this, you get a minus sign that comes down, two m's that come down, and then you cancel out the G dependence, and so you get the minus right here. Okay. So this is what you have right there, and you will notice that this is exactly Bessel's formula, and so f has to be a linear combination of two Bessel functions. So we use the J Bessel functions and the Y Bessel functions. Why do we do that? Because the Y's go to 0 and rho is equal to 0. So we can eliminate those, these, by setting B is equal to 0 right there. All right. So that simplifies F down to this. And G has to be equal to this. All right. Same thing as E to the J and phi. You can write it as sines and cosines. All right. So now we have two solutions. Y1 and psi1 and psi2 here. So we have with cosines and with sines. All right, and so now we need to have it such that at rho is equal to a, we have 0 here, so this has to match the boundary conditions of our electric potential, which has at the walls of the cylinder of a potential of 0, so we have to have the same thing for our size. And so what that does is that determines what my value here is within our eigenvalues. And we find that the eigenvalue has to be equal to this, where these are the zeros of the Bessel function. All right, and here's a plot of the zeros of the Bessel function. We have to normalize these functions, these eigenvectors or eigenfunctions. So that's not so difficult to do. We can easily do that. And we find that my a's that normalize this are given by this, so that we can write then phi1 as this and phi2 as this. And those are now fully normalized in two different solutions. Okay. So we have found the eigenfunctions and the eigenvalues. We found the eigenfunctions and the eigenvalues. All right. And so now the Green's function reduces down to this right here. This right here. All right. And so once you do put that in, you get indeed this. All right. So that's what you get, and so you can use a little bit of trigonometric formulas to get that the Green function reduces down to a single cosine here, which is symmetric with phi and phi prime, which you expect. So everything's now symmetric with interchanging the primes with the unprimes. All right. So now, now that you have that Green's function, you can put in, use that with any charge distribution you want, and be able to find the potential. So it's quite a powerful technique. But of course, the difficult task then is to actually perform that integral. So that was the series form for that example. All right. So it's a little bit odd why they wanted us to find. They have that example within the section that tells you how to find the closed form for the two-dimensional Green's function, because we found it with series form. So now let's start the series form. All right. So the series form is, as we've learned before, we write the Green's function as in the form of a series of terms of these eigenfunctions, and the coefficients then turn out to be this right here for 1D problems. All right. For two-dimensional problems, the bilinear formula is very similar, except now you have a double summation, and you will have more eigenvalues. You'll have eigenvalues that depend on the index m and n. All right. Of course, they have to satisfy the same boundary conditions. They have to be normalized. Everything you would expect. So we can start with an example of 2D Green's functions. Again, the static fields. So this is what we have for the static fields, where V is a potential distribution and Q is the charge distribution. The Green's function will satisfy, of course, this equation here, where we replace the right-hand side with the delta Dirac functions. It has to obey the same boundary conditions. And then once you do that, the potential will be equal to this. And that's what we had in the closed form solution as well. V was equal to that. And the task was then to find G. Okay. So we go back and we need to look at the homogeneous equation of 1572 of this. So we find, and we need to now find the eigenfunctions and eigenvalues, subject to the same boundary conditions. Okay, we go about this in the way, at first, in a very similar way. Where we first cast this equation, any one of these equations, G or this one here, in the form of a Strohm-Liouville. All right. Say the G, for example, or say this original one right here. All right. So we do that, and we have to then find what is P, Q, and R, and so this is what we have to find this. And then we can solve for this right here, and move forward. So actually, you really don't need to do this all this much for the series form. The only thing you need to do for the reason you would do this for the series form is so you can more accurately determine what the lambda is for the G equation, which lambda will be 0. There is no lambda on this side here. And so you're going to have no lambda that comes into our bilinear form for this equation. So this is going to be 0, as we're going to see later on. All right? And so you're only going to have a minus lambda mn here. But you're not going to let r be identically 0. Instead, you're going to let r is equal to 1, and then our lambda in the ends for the homogeneous solution is going to be within there. Okay, and then from that you get this right here. Okay, because with r is equal to 1, you get this plus. You're going to bring that term over to the other side, and then that's what you get. All right, this might have been a little bit confusing because we say solve the homogeneous problem right here, but this isn't homogeneous. You have this on this side. Homogeneous form is where the right-hand side is 0. So that's because this initially would go over to this side, and you would have 0 over there. And it's because r is equal to 1. All right? So it's a little confusing, but if you go through and are systematic about it, you find that this is the homogeneous form of the differential equation, and then you need to solve this for the eigenfunction psi and the eigenvalues lambda. Good. Okay. We start this with the same sort of thing as before, but now it makes more sense when we're doing the series. We have to solve for psi. So we do that in the separation of variables method by doing a trial solution like this where we separate out the dependencies. And we get that f has to be equal to this and g has to be equal to this, but now we can apply the boundary conditions. So the boundary conditions at x is equal to 0 and x is equal to a has to be equal to 0. So that says our cosine term has to be eliminated, so a has to be 0. And C has to be 0. So A has to be 0, C has to be 0. And for x is equal to A, we need a 0 as well. That helps us determine, doesn't help us, that lets us determine P is equal to n pi over A, and Q is equal to n pi over B because of this boundary condition. Okay, so once we have that, these are our solutions so far, except for now we have to normalize them. So we have to, that will determine those coefficients that are out in front of the two sides. So you normalize it by integrating over the area of our domain. That area has to be equal to 1 if all the indices are the same, and 0 otherwise, and we're able to then find that those b's are 2 r squared to ab. So we plug that back in here, and that is those are our eigenfunctions. So we put those directly into the bilinear formula right here, and bingo, that's what we have. Okay. Okay, but for the electrostatics, which is what we were working on before, what we're working on now, I had made a big point of saying my lambda is equal to 0 here. All right, and so this for electrostatics is equal to 0. Okay, so they still have the lambda here. For this, but then this is where they say for the static case, lambda is equal to 0. All right. So once you have that, then of course, as we've said several times, you can find V for any charge distribution Q. Okay. So time harmonic fields. Good. So now we do not have static. We have a time harmonic field. So how does that change things? Well, it introduces a term like this. And this is where our lambda now becomes non-zero. So we'll see that in the denominator in the series forms, we'll have lambda in there where we let it be equal to 0 before. That's really the biggest change. Otherwise, everything's pretty much the same. In this example, we're looking at electric fields in the z direction, and on the right-hand side is what produces those electric fields, some sort of current density in the z direction. All right, so let's say we have those boundary conditions. This can represent the electric field of a TMZ field mode with no z variations inside a rectangular metallic cavity of dimensions A, B, and C. The F being this can represent the normalized electric current density, and the objective is to find the Green's function and ultimately E sub z. All right, so say we have something like this. So we have boundary conditions that must exist on E sub z. E sub z, so at the walls, x is equal to 0, x is equal to a. You have to have E sub z being 0. And same as for the top and bottom walls. Y is equal to 0 and y is equal to b. E sub z has to be 0. All right. So this is the function that has to be satisfied. We're replacing the j sub z term on the right-hand side with delta functions. But now we have this being lambda, beta squared. G, of course, satisfies the same boundary conditions. And then once we know G, we can figure out what E is. Okay, so let's find G. Series form. All right. So the series form. Again, we look at the homogeneous solution. Okay, so this is where we do it properly. My R is equal to 1, and then where we set the right-hand side to be equal to 0. This is the homogeneous form of that differential equation that we're working with now. And these are our eigen values. So this is lambda mn, and these are our eigenfunctions. All right. Subject to the same boundary conditions, of course. And all right. So we have to solve for psi. So it's fairly easy to solve for these. It has to be 0 and x is equal to 0, y is equal to 0. So that eliminates any cosine terms. So we only have sines here. And because psi has to be 0 at x is equal to a and y is equal to b, you find that beta x and beta y have to be this. All right? Okay, fine. You normalize psi. All right? Very easy to do. In fact, that's what they do right here. Very easy to normalize psi, and you get this as the eigenfunctions. These as the eigenfunctions. And then previously you figured out what lambda is. It's beta squared, beta mn squared, and the lambda in the Green's function is just beta squared. So you can go directly now to the bilinear formula and plug everything in, and bingo, that's what you have. So that's the Green's function. And you can put that in to our equation for E sub z. Put that in here, and then for any charge distribution, current distribution, you can use that with G to find out what E sub z is. All right. So this is sort of interesting. Obviously, the Green function possesses a singularity when beta is equal to this right here. So going back to that form, when beta is equal to with the square root of this, so or when beta squared is equal to this. All right. What that gives you is is a resonance. So at resonance, you're going to be feeding the cavity, and the field is going to be getting larger and larger and larger, and as a function of time, and it won't be simply time harmonic fields anymore. So the whole thing breaks down. So that's what they say throughout the next few slides, is that's what's going on here. At those eigenvalues, for which you have a resonance, you have singularities in the Green's functions, the frequencies of this excitation sorts match the natural frequencies of the system. This is referred to as a resonance, and the fields will continuously increase without bounds in the limit reaching values of infinity, exactly what I said. For those cases, no steady state solutions exist. One way to contain the fields is to introduce damping. In practice, for metallic cavities, damping is introduced by losses that are due to non-perfectly conducting walls. And the higher the fields, the more loss you have in the system. So after a certain amount of time, the energy you feed into the system will be equal to the energy being absorbed by the lossy walls. But if you have a PEC, that doesn't happen. And then So at those resonances, you have to be a little bit careful. That's fine. Okay, so that is for 2 dimensions, x and y. So now we need to go on to full 3 dimensions as well, and then look at Green's functions for the full scalar Helmholtz equations in 3 dimensions, both using rectangular coordinates, cylindrical coordinates, and spherical coordinates. All right. To do so, however, we have to do a little bit more math. In studying Green's functions and some other identities called Green's identities to help us with that. Excuse me. So that's what we're going to do. Green's identities and methods. So now that we have derived Green's functions both for 1 and 2-dimensional space variables and rectangular coordinates for this general Strom-Liouville self-adjoint operator L, let us generalize the procedure for the development of the Green's functions for the 3-dimensional Helmholtz partial differential equation. Okay, so full 3-dimensional. So how do we do that? Well, we need some tools, some techniques, some identities, some to work with this. So this is the differential equation we're going to focus on, and we are going to allow for mixed boundary conditions. And so meaning that the function itself and its derivative, this really should be, yeah, of course this has to be that, or for this to make sense. Where RS is on the surface and N is the outward directed unit normal of that surface. These are also called impedance boundary conditions. All right. So right now, alpha 1 and alpha 2 are totally unspecified. You can have one being 0, the other non-zero, over the entire surface, or you can have the other be 0, and the first one non-zero for the entire surface, or a whole mix of it. So we'll go over every single example. So Helmholtz. So we're going to be looking at that. So the Green's function for that, we replace the right-hand side, whatever's on the right-hand side, with the delta function. And so G must satisfy that equation. With the same boundary condition. All right, has to be the same boundary condition. We're eventually going to loosen this up a little bit to have somewhat different boundary conditions under some very specialized situations. All right, so the first thing we have to do is get some tools in our tool chest, and that's the Green's first identity and Green's second identity. So let's calculate those first. Okay, so we're going to take a look at a volume, this volume right here. And we have conducting bodies within this volume that has surfaces S1, S2, all the way up to Sn. So we have N bodies. Now, by appropriate cuts, the volume V is bounded by a regular surface S that consists of S1 plus S2 plus Sn, plus surfaces along the cuts, and SA, the infinite radius sphere that encloses all the conducting bodies. So this volume here is enclosed by this S, that goes out to infinity, and these types of S's, and then the S's around the objects, like this one here, and this one here. All right, so those are all the different types of S's. The SN's right here, along the cuts, and along the infinite radius sphere that encloses all the bodies. And N is the unit vector normal to S directed outwards. Now contributions along the cuts cancel out, of course, because they go in opposite directions and they're right up on each other. All right, like this. So any integral from those two will cancel out. And again, any integral over this path will cancel because the functions will go to 0 as my r goes to infinity. All right. So let us introduce within V two scalar functions, phi and psi, such that within V and on S, phi and psi are continuous, and the first and second derivatives of phi and psi are continuous. Okay, fine. So now we're going to work with this function itself, this function, phi, del, psi, and we are going to apply the divergence theorem. So we have this, and we do an integral over the entire surface, and we apply the divergence theorem to say that this is equal to this. That's fine. And now we're going to, this right here, we're going to use this vector formula. It's very easy. Basically, del, this right here, if you, basically product rule, essentially. And you find that it's equal to this and this, all right, where this right here is just del squared. And so we replace that, so we use this right here instead of this on in the volume integral, getting this right here. So that's easy, extraordinarily easy. That's called Green's first identity, all right? Well, we can also look at this a little bit more. We can say ds, so we have a vector dotted into ds. That ds has a normal vector in hat. So by dotting this with in hat, that gives the directional derivative in the direction of the normal vector of the surface that we're on at that point in the integration. All right, so that's generally noted as d psi over dn. So where the derivative d psi dn is taken in the direction of the positive normal, and so we can write Green's first identity like this. All right, same thing, it's just an alternate form. Okay. Okay, so we started off by looking at this function. We can now, likewise, look at this function, this vector function, all right? And that's what we do right here. We look at doing the same thing with that function. And so when we do that, we get either this, which we can express as this as well. And that's, again, Green's first identity. But now we have these two, this and this. And we can subtract the two of them. And this is a common term, this right here, to both of them. So when we subtract that from that, this term will cancel out, leaving only that term. So we have the two terms that have within it the del squared, but the other term falls out. So this is what we have on the right-hand side. The left-hand side is this right here, and this is called Green's second identity. And likewise, just as you did before, you can let these be d psi over dn's, d phi over dn, but now this is a scalar. But my n is the outward pointing normal vector of the surface, and so forth. So that's what we have for Green's second identity. So the first identity is this right here, and the second, or the alternate, and the second identity are these two. All right. So we're going to use these now to develop the Green's function. So now let's get on this. Let's develop the Green's function. Um, with the introduction of the Green's first and second identities, we are now ready to develop the formulation of the generalized Green's function method of phi for the partial differential, the Helmholtz equation, right? So we're going to do that, and so the Green's function has satisfied that differential equation, three-dimensional, second order, partial differential equation. So, okay, so the approach for this is we have these two equations, right here and right here. To this equation here, we multiply by g, capital G. To this equation, we multiply it by phi. So, and then we get these two equations here, all right? We are now going to subtract the two. Subtracting those two equations and doing the integral all at the same time. So we get, so we subtract these two, and so you're going to get and integrate. So this falls out because we're subtracting, and this obviously doesn't, this obviously doesn't, this doesn't, that doesn't. And so on that left-hand side from the previous slide turns in the right-hand side of this slide and gives you that. And the right-hand side of the previous slide gives you the left-hand side. I wish they wouldn't have done it that way, but they did. Of this, but this is a delta function integrated over the entire volume. So this simply becomes phi of r. And then we can bring this over to the other side, and so we get phi is equal to volume integral f over g, volume integral of this right here. And so now we use Green's second identity to say what this is right here, and so we replace that. And so using Green's second identity, we have that phi is equal to that, where we still have phi within the function r prime, at being a function of r prime. But it doesn't really matter. These are symmetric. You can replace r with r prime and r prime with r and have it not impact that function at all. R is simply a dummy integration variable, so we can have that as r prime as well. And so we can switch r's to r primes to r, perfectly fine without it impacting anything. All right? And so, and likewise, with the differentiation. So this is what we have. Yet another typo here, because there's supposed to be a prime right there. There's just a lot of typos in this. At some point, I have to go through and make my own slides, but it'll take eons to do this. Yeah. So this is what we have then for the solution of the three-dimensional second order partial differential Helmholtz equation. Quite something. So we have the thing that involves the volume integral, where we have this excitation source for this driving function, and we have to integrate that multiplied by something, and that something is a Green's function, over the entire volume. But then on top of that, we have this right here, where we have surface terms, where the surface impacts phi. And so that's also involved in this calculation, all right? But this is where our boundary conditions come in, because quite often this is 0, or this is 0, or this is 0 on the surfaces, all right? Or this is 0. So we're going to look at each one of those situations. So when we have mixed boundary conditions, it is desirable, if possible, to find the Green's function which vanishes on part of S, for which we know phi, and which has a normal derivative equal to 0 over part of S, for which we know d phi dn. We will see that the Green's functions are useful for solving boundary value problems when the volume distribution of charge rho is 0 as well. Yeah. So that's interesting. So when we have 0 being within here, then this whole term is going to fall out, but yet we can still find phi, obviously, from what happens right at the surfaces. So that's what this is saying right here, of course. So solution of Helmholtz differential equation. So this is what we have. And this is a generalized formula for the development of Green's functions for a 3D scalar Helmholtz equation. It can be simplified depending on the boundary conditions of phi and g and their derivatives at s. The objective will be to judiciously choose the boundary conditions on the development of g once the boundary conditions on phi are stated, so as to simplify, if not eliminate, the surface contribution. All right, so anyways, quite often we go to links to try to figure out how to eliminate this second term, or at best minimize it. I mean, or at a minimum, minimize it. So, in practice, we usually know phi on part of the boundary and d phi dn on the other part of the boundary. However, by a suitable modification of the Green's function, it is possible, in principle at least, to obtain a solution for phi from the knowledge of either phi or d phi dn on the boundary. Right. So if the required boundary condition specifies a value of phi on the complete boundary, this is said of, as we know this, it is called Dirichlet boundary condition. Not Dirichlet, but Dirichlet. So, and if the normal derivative d phi dn is specified on the entire boundary, the corresponding boundary condition are referred to Neumann boundary conditions. And if you know phi on one part but d phi dn on the other remainder, then we have mixed boundary conditions. We've said this before. All right. So this is what we have in math. That's what in math what I stated is expressed here in math. All right. Green's function has to satisfy the same boundary conditions, unless we'll come across some cases where we don't have the Green's function obey the same. But for the most part, it should, to make things easier. Okay. So let's look at case A, non-homogeneous partial differential equation with homogeneous Dirichlet boundary conditions. Okay? That's easy because now Dirichlet says we're going to have 0 on S, and then we want to construct a Green's function with the same boundary conditions. So therefore, we have 0 here and 0 here, and this whole surface term falls out, leaving this right there. Very good. Very good. For these boundary conditions on phi and g, both terms in the surface integral vanish. So we have that for the for phi. In many cases, the bilinear form of 15.61 and 15.94 are equivalent in the desired coordinate system and number of space variables. It is appropriate for forming the Green's function. Its existence will depend upon the eigenvalues of the homogeneous. So you can either use the bilinear form for the series, uh, or the closed form for figuring out the Green's function. And then applying this equation. So you can find then Green's function in any way you wish, just so that it satisfies this boundary condition on the surface, and then you'll be able to figure out, use this equation to figure out phi for any driving function f. All right. So now we have the same non-homogeneous PDE with Dirichlet, or non-homogeneous Dirichlet problems. All right. So this is where we have non-homogeneous Dirichlet problems. So if the non-homogeneous form of the PDE satisfies the non-homogeneous Dirichlet BC, so say we have it not being 0 but G, or this also could be 0 over some portion but a non-zero over others, this is the exception where we can say, well, we can still construct a Green's function that satisfies this boundary condition. We're free to do so, actually. Okay? But what happens then is that when we use that Green's function, we not only get this, but this is going to be non-zero over certain portions of the surface. So that part of the surface integral needs to remain. But that's fine. If we know this, then that's perfectly fine. But G has a boundary condition of being 0 on all the surfaces, but not del G. So our general equation can accommodate non-homogeneous Dirichlet boundary conditions, where we let G be 0 everywhere on S, but my phi's may not be 0 everywhere on S. So that's why this portion of the right-hand side remains. All right, case C then, we have homogeneous norm and boundary conditions. All right, this is going to be fairly simple as well. So norm and boundary conditions, this says that d phi dn is equal to 0 on the surface. All right. Okay, but now there is one complication with this. So we cannot construct a Green's function with dg and dn being equal to 0 over the entire surface. All right, we cannot do that. And because it will turn out that my d phi dn, my dg dn has to be equal to something like this, 1 over s, where s is the surface of the area of the surface. All right. So in the end, so I think that they must derive this. Yeah. So we're going to see that this is what we have. All right. In the book, they go through and explain it, but they jump ahead to the solution right here first. And so this is what we're going to get right here. But just hold on, because you'll see why this is the case. So there's the part of the general solution. Where's the last time we've had the general solution? Right here. This is going to be 0 in that case. But this is not going to be identically 0 over the entire surface. All right. In fact, this is going to be equal to 1 over s naught. And so 1 over s naught. All right. So now our task is to figure out why that's the case. When the norm and boundary conditions are involved, the solutions become more complex, primarily because the normal gradients of phi are not independent of the partial differential equation. If the homogeneous form of the PDE satisfies the homogeneous norm and conditions, then we do indeed have this right here. All right, but we cannot impose the same boundary conditions for G, and so let's show why that is. So we do that by saying this becomes evident from what follows. This is accomplished by using the divergence theorem. So we start with this right here, the divergence theorem, and we apply the divergence theorem to del G. All right, del G, that vector, and we get this right here. So we take the volume integral of the original differential equation, and so this is 1 right here, all right? And we apply the divergence theorem to this right here, and this is what we have, all right? Where we have the del dot S right there, all right? So if we choose this, which is involved in this portion right here, to be uniquely 0 over the entire surface, then what this says is that this imposes the condition of this, which cannot be satisfied if beta is 0. So if beta is 0, then this can't be satisfied. 0 is not equal to 1. And this has you have to be able to allow for beta being equal to 0. And so that excludes the possibility of setting this to be uniquely 0. So we can't. So when beta is equal to 0, all right, so then this will fall out, and we have this right here, all right? And or we have that this integral then, which then you just can equate that to del dot G, the average value over the surface area of the surface is equal to 1. So therefore we can state that, we can choose to state that del G is equal to a constant, okay? This is a choice. That still allows for us to have beta to be equal to 0. We can choose that del G is equal to 1 over S naught, where S naught is the area of the surface, okay? So then this is what the final equation becomes for the computation, the evaluation of phi. The second term on the right-hand side is a constant and can be dropped. So this ends up to be a constant, all right? It's a constant value. It doesn't depend on R. And so it can be dropped because we're always interested in differences in potential, not absolute values of potential, but differences in potential. So an additive constant is meaningless. So, all right, we have a type D, non-homogeneous, but they go on to say it's generally, so we have non-homogeneous mixed boundary conditions, all right? And so they basically say, don't worry about it so much. And it's generally the case. Almost all the time, you're either working with directionally or northern boundary conditions. And so we're not going to go over it very much. It's mixed. All right. So as an example, let's look at Poisson's equation. All right. Yeah, Poisson's equation. Let's see how we're doing with time. 9 minutes. All right, not bad. So we want to find the potential phi given a certain charge distribution rho. All right. All right. So we've had this in electrostatics for a long time. You will have learned this in first semester electrostatics, and you will know that the formula, given this equation, the formula to find phi is equal to this right here. And so you will now recognize that this is the Green's function. But we have to show that. and this is true for any coordinate system that we use. All right. So we may derive different versions using enclosed form or series form or something else, where we get a different functional form here of G that's not expressed as 1 over 4 pi r. But at the end of the day, we will find that they are identically equal to 1 over 4 pi r, with r being this. All right. So we're going to go about solving for this. So Green's function must satisfy this partial differential equation. And what we can show is that just what I said, the Green's function turns into this right here. All right. So this is the volume part of this, but the surface part of it, if we were to keep that, would be included like that right there. All right. So we can add that in there. Normally in undergraduate electrostatics, we don't have surfaces. Our surface goes to infinity, and phi and g's, d phi's, dn's, dg, dn's all go to 0. But if we do have a surface, then we have to pay attention to that, and then this is the full equation for phi. All right. The previous equation is not necessarily very useful because it requires that we know both this and this. Yeah, okay. On the surface. In practice, we usually know phi on the surface, or at least on part of the surface, but generally everywhere. Let's say it's a conducting sphere of some sort, a conducting surface where we ground it, for example, or d phi dn on the surface. So if phi is known over the entire surface, then the term d phi dn can be limited by making the Green's function vanish on the complete surface. So we have the boundary condition such that g vanishes on the surface, and then that eliminates this second term. All right, and then we can compute this term then, and then this will be given to us because it'll be told to us by the problem. So then this is the equation. If d phi dn is known over the entire surface, then the term phi can be eliminated by doing the opposite, by letting dg over dn vanish. So we can do the opposite. Again, reducing down this second surface integral just to one term. Needless to say, quite often in practice, it is about as difficult to find a solution for the Green's function as it is to solve the original boundary value problem. But we've already discussed the advantages of the Green's function. It allows for you to put in any driving condition, in this case a charge distribution, and use the same Green's function in the evaluation for phi. All right, so it converts the second order partial differential equation over to an integral problem. So that's very useful. So the use of the Green's function converts the differential equation together with boundary conditions to an integral equation, which in many cases is more readily attacked with approximation techniques. All right, so now we're ready to look at the Green's function for the scalar Helmholtz equation, three-dimensional and time harmonic in rectangular coordinates. So we're going to look at a rectangular waveguide excited by a linear electric probe. Okay, so this is going. So here's our probe in the y direction, and we are going to be exciting an E of y, and it's time harmonic. So this is, so we have a beta naught squared. For our time harmonic solution, it's excited by this current. So this is the differential equation. And then we have the walls of the cavity that force E of y to be 0 when E of y is tangent to the walls. So at the right and left walls, E of y has to be equal to 0, so that x is equal to 0 and x is equal to a has to be, E of y has to be 0. So E of y represents the electric field component of a TMZ field configuration inside the metallic waveguide of dimensions A and B in the x, y directions respectively, as shown in the figure. Also, J of y represents the electric current density of the feed probe that is used to excite the fields within the metallic waveguide. Yeah, fine. We knew that from prior chapters. So we're going to assume that the wave is then traveling in the z direction and is time harmonic. So this is what we have for the Green's. So then we develop the Green's function. The Green's function has to satisfy these two conditions. So these two boundary conditions. So it has to satisfy this, and it has to satisfy this. So, since the electric field and the Green's function satisfy respectively the Dirichlet boundary conditions, then according to 15123 and 15125, the electric field, then of course once we know, so it satisfies the Dirichlet boundary conditions, and so therefore our E of y reduces down to this, all right, where we only have the volume interval part. So the Green's function can be derived either in closed form series or integral form. We choose the series form for this. So the series form. Okay, good. To begin the development of the Green's function, by assuming its solution can be represented by two function Fourier series. All right, both the sine function in x and the cosine in y. So, so we first start off with the series form of the Green's function by first assuming a series, in this case, okay? And that's even before we get to the homogeneous equation that we need to solve for to allow for us to use a bilinear form, okay? So by choosing sines for x and cosines for y, we are able to satisfy the boundary conditions at x is equal to 0 and x is equal to a, all right? And so, and then we have additional boundary conditions, and the additional boundary conditions would state that we have to have, like the magnetic field has to be 0 at y is equal to 0 and y is equal to b. But in terms of E of y, it turns out where we need the cosines here. So we sort of do a trial solution where we have g being equal to this times amplitude or coefficient in front of our sines. All right, where m and n are integers that we're summing over, and these are the coefficients out in front. Okay, so then we substitute that trial solution into the differential equation that Green's function must satisfy, and then we have that. Okay, and that's fine, and we're going to now multiply both sides by this and integrate from 0 to a in x and 0 to b in y. We have a delta function, delta x, delta y on that side. So those volume, that surface interval, which really turns into a surface integral, turns into this. and so this is what we have. And so now we see that this is the equation that G must satisfy. Sorry about the dog. So, so this is the equation G must satisfy, and it has a delta over here. It has a delta over there. And so my beta z is equal to this, and my beta x is this and this. So the function g of m satisfies a single variable differential equation and can be found using the recipe for a closed form. All right, so now we can use the closed form and of the two. So now we have the closed form, and so we're going to find the two solutions that satisfy the homogeneous equation for z being less than z prime and z being greater than z prime. Okay, so this is extremely easy to do because we have the plus here, so we can either use sines or cosines, or e to the j, e to the minus j, and we choose the e to the j, e to the minus j solutions for this. And so these are our two solutions. For z is less than z prime, z is greater than z prime. We're going to find the Wronskian of these two solutions, and so we do that, and this is what we get for the Wronskian, and so for the closed form, we need to figure out what P, Q, R, and F is. We've already talked about how to do that. We find that P is equal to 1, R is equal to 1, Q is equal to 0, and lambda is equal to beta z squared. So we have everything we need to plug this in to find what the G's are using the closed form recipe. This is what we get. We can combine both of these to be this right here. And so that is my G. Then that goes into the original summation with the sines and the cosines. All right. And so that is my G then for this scalar Helmholtz equation for rectangular coordinates applied to this particular problem, a waveguide with a wave traveling in the z direction. Okay. So cylindrical coordinates. So let us assume that we have an infinite line source of constant current I sub z, and it is placed at rho is equal to rho prime, phi is equal to phi prime inside a circular waveguide of radius a, as shown in the next figure. We're going to assume that the waveguide as well as the line source are infinite in length, and therefore the problem will reduce down to a 2D problem. So we've already done this problem before, but we're going to do it again and in a different way. So this is what we have. 2D problem. We're going to reduce down to a 2D problem because it's infinite in the z direction. But this is the equation that we have. It needs to be satisfied. Boundary conditions have to be upheld at the walls of the waveguide, and so this is what we have right here. And so for the Green's function, we have the right-hand side being replaced, the function on the right-hand side being replaced with the delta function, and this being the boundary condition. Since the boundary conditions of E of z and g are Dirichlet type, then according to 123 and 125, we don't have to worry about any surface terms. We can just look at the volume integral, which turns into a surface integral for 2D. So now we're going to look at closed form. So we're going to solve this for the closed form. All right. So assuming a 2D problem in Z, we can initially express the Green's function by an infinite series whose eigenvalues in phi must satisfy periodic requirements. So we're first going to get rid of the d phi terms in our del squared term by assuming that G has to have this form here, all right, with coefficients in front of this. So, so we do that. We also note that in cylindrical coordinates, my del is equal to one of these. In general, it's equal to this, but if there's no z dependence, it's equal to this right here. If there's no phi dependence, it's this. If there's no phi, no z, there's this. So we don't have any z dependence here, so it's either going to be one of these two. But if we allow for phi dependence, we'll use that bottom one, all right, which we do. We allow phi dependence. So on the del function on this side here is 1 over rho, del rho minus rho prime, del phi minus phi prime, okay? But now with that, we take two derivatives of e to the j m phi, and we get a minus down here, and we get the m squared. And then this will cancel out. Well, we're going to integrate both sides. So now we use the integral right here, and integrate from 0 to 2 pi over phi. And so then we select out a single m value here, and we get rid of this function, and we also get rid of this, resulting in this equation that needs to be satisfied. So we get this equation that needs to be satisfied, which, rearranging this, we get this right here. So this is Bessel's equation. So now, okay, so this is what we have at this point. So right here, now we're going to look at the homogeneous equation of this, where we set this side here to be equal to 0. And now this is where we're going to find the two terms that satisfy this. So the function gm satisfies the differential equation of this right here, all right? And a solution can be obtained by the closed form recipe represented by 1544C. The homogeneous equation can be written as this. So we get rid of the right-hand side, and now we deal with this homogeneous solution. And so in the closed form, we need those P, Q, R, and lambdas, and we find out what those are, so that we know what the Strom-Liouville form of Bessel's equation is, and it has to satisfy the same boundary condition. So it has to be finite at rho is equal to 0. So that means my beta is 0 for rho is less than rho prime, but not necessarily for rho is greater than rho prime. Okay, because we're excluding the origin in this part here. Okay, it has to satisfy the boundary conditions at rho is equal to A, though, which means that G at rho is equal to A must be 0. So we have 0 at rho is equal to A, and so we can figure out what D is in terms of C at least. So thus we reduce this down to this right here. For rho is equal to rho prime. Rho is less than rho prime. We have this solution. For rho is greater than rho prime, it's equal to that solution. We need to find the Wronskian in the closed form recipe. And so we do that. We find the Wronskian. The Wronskian after we use some identities of Bessel functions, reduces down to this form here. And then we can go and write down the solution for the G of m's, being this for rows less than rho prime, and this right here for rows greater than rho prime. Okay? So that's a lowercase g. So we put that lowercase g back into here, along with the e to the m phi's in the summation. And this is what we have for the capital G. And so that's the capital G. And then with the capital G, we can use that with the original equation to figure out what the E of Z is as a function of current, I sub Z. All right. Let's see, now we have an example. Okay, so now that we know the Green's function, we can do this example. An infinite electric line source of constant current I sub Z is located at rho is equal to rho prime, phi is equal to phi prime, as shown in 15-9. And it is radiating in an unbounded free space. Derive the Green's function in closed form. So since the line source is removed from the origin, so it's radiating an unbounded free space. All right, so there is no walls for this example. So since the line source is removed from the origin, the Green's function must be a function of phi and phi prime, and it must take the form of 151. So let's go back to 151. Right. So it must be, where's our 151? Here's 151. It must be of this form here. All right. So here's our phi prime dependence. Here's our phi dependence. Wow. Okay. And it satisfies the differential equations of these. This right here. All right. So this is what we have. This is the geometry, but it's unbounded. There is no containing sphere, and so that's what we have. So E sub Z must vanish at rho goes to infinity. So that is a boundary condition. E sub Z must vanish at rho as rho goes to infinity. So here's our differential equation with the line source being at rho is equal to rho prime. And so our Green's function must satisfy this right here. We have no Z dependence, so this is what we use. And the G also has a radiation boundary condition. All right, so this is what the Green's function must satisfy. In cylindrical coordinates, this is what we have. And so we have the trial solution here. And then we plug this trial solution here into this to get this right here. We're going to multiply both sides by e to the minus j n phi and integrate over 0 to 2 pi and use the orthogonality condition and this to be able to get to this equation right here, which gets you down to this equation. All right, for lowercase g sub m. All right, and so now we can use. So this is what we get. We've stated this before, and from the prior slide, we get this for the homogeneous equation with the radiation boundary conditions. And so we can now solve in the closed form. All right. the fields must be finite at rho, so we need two solutions. One for rho is less than rho prime, and one for rho is greater than rho prime. So for rho is less than rho prime, we use this right here. And because these Bessel functions go to infinity at rho is equal to 0, therefore we can get rid of those by saying b has to be equal to 0. So my first solution is this. For the second solution, for rho is greater than rho prime, we are going to have outward traveling waves. So outward traveling waves are represented by the Hankel function of the second type, h2. So this is my y2. Okay. So we figure out the Wronskian of this, and we figure out that the Wronskian is this right here after a little bit of work and some use of Bessel function identities. And so this is what we have. Thus, g of n can be written using this. So we have this being lowercase g, and then we put lowercase g back into the summation. That includes the e to the j n phi with the summation. And this is my capital G. All right? So where we've used the property of Hankel functions, the addition theorem for Hankel functions within this right here. What is it? It was this right here, actually. Yeah. To simplify the Wronskian, we use the addition theorem for Hankel functions. No, actually, no. We're going to use the addition function for Hankel functions to simplify these two things right here, to get g to be equal to this. Let's go back. Right. Yeah. So this whole thing, using this, reduces down to this right here. Yeah, so that's impressive. So this Green's function can be expressed in succinct form as that, which is a well-known two-dimensional Green's function for cylindrical disks. It's great. It's great. Nice and compact and tidy. Very nice. So that's our Green's function. And so with that, then, we can figure out what E sub z is. So, very good. So spherical coordinates. Spherical coordinates are more complex. So let's go through them. The development of Green's functions for problems represented by exactly what I said. Spherical coordinates is more complex and must be expressed in terms of spherical Bessel functions, spherical Hankel functions, Legendre functions, and complex exponentials. In order to minimize the mathematical complexities, we will develop the Green's function of a source positioned at r prime, theta prime, and phi prime inside a sphere of radius a with free space as shown in 1510. Okay, so this is our spherical coordinate system, as you know, but obviously this is the polar, the azimuthal angles, and the r. All right. So the Green's function must satisfy the partial differential equation of this, of course, subject to the boundary conditions at r is equal to a, that the Green's function must be 0. So in spherical coordinates, the delta function is equal to this, depending on the types of dependencies on theta, phi, and r. And in expanded form, the Green's function can be written as this, where we express the del squared operator in its proper spherical coordinates. and then this is so this is what we have, and then we do a trial solution. A trial solution that involves a summation over spherical harmonics. Okay, because spherical harmonics form a complete set for the functions of the angles theta and phi, such that we can write the Green's function as a double summation over this. Okay, where we either express it in this way, or in E and M we call this combination tesseraal harmonics. All right, so our tesseraal harmonics, even and odd, are given by this, and they're normalized, so they're not straight equalities of the P and E to the J, but they have these coefficients out front given by this. All right, so multiplying this equation by r squared and substituting this into the equation as well, we get this, and now we're going to, so this is what we get. Okay, and so now this is where they start making errors in this section. They say at this point we're going to divide both sides by this. So they're going to divide both sides of this equation by GMN TMN, right? Yeah, and then take that into the into the summation. But if you think about it, that doesn't make any sense whatsoever. Because you can't do, you actually mathematically cannot do that. That's not a valid mathematical operation. And so, but what you can do is take out G of M and T of M internally for each term. And what you want to do in the next couple of slides is work with this term and this term within the summation. All right? So we're not going to do what they say here, divide both sides of the equation by GMN and get this, because that is mathematically incorrect. All right. So the GMN stays within here. All right, think about what I'm saying. But it doesn't matter, because at the end of this, they get the same thing, because they're trying to express this these two things in a different way by combining them, and you can still do that by just looking at this and taking out a GMN TMN from this. So if you take this thing all the way out and put it out in front, you still get something that looks like this, but you get the GMN TMN right in front, and then that's changed and that changed, because what they want to do now is to be able to say those two terms equal this right here, this minus n plus 1, so that we can replace that more complicated two-term things into one and express this like this. Okay, so they made a couple of mistakes, but in the end, this is the correct formula, and this is what you have. All right, you still have to look at the tesseraal functions, or orthonormal basis functions. Those are perfectly fine. And so with the G's, we're also going to let them be tesseraal equations, but the G's have dependencies on r and r prime, and theta prime, and phi prime. And we're going to assume that we can do separation of variables to take out the r dependence from the theta prime, phi prime dependence, and express that as a tesseraal function as well, which we should be able to do that because of the fact that the Green's functions must be symmetric with respect to theta, theta prime, and phi, phi prime. All right, so the G's must have a theta prime, phi prime dependence that corresponds to a tesseraal function. All right. So then we can multiply both sides by this and integrate from 0 over 2 pi, and using the orthogonality relation of tesseract equations, we get this right here. That must be satisfied. All right. So then we're down to the standard thing of saying, okay, let's solve this in, say, the closed form recipe. So for that, we have the homogeneous solution, and we have to find what P, Q, R, and lambda are, so that we can fit that equation into the Strom-Liouville form. And so that's fine. We can do that. And we use that method that we outlined in the last lecture to find these correspondence. It's perfectly fine. And then so now we have to deal with this equation here and find the solutions. And so the solutions to those are spherical Bessel functions. So they're spherical Bessel functions, and we have two solutions for that. Ones that are valid here and here, all right? For r is less than r prime, for r is greater than r prime. So we have two solutions, H1 and H2 for r less than r prime and r greater than r prime. All right. So same thing as with the cylinder. The solution for r less than r prime has to remain finite at r is equal to 0. Therefore, my this has to be 0. And so also must satisfy the condition at r is equal to a, that H2 is equal to 0, so that helps us eliminate D. And so these are our two solutions that satisfy the boundary conditions. So now we can find the Wronskian and use some properties of Bessel functions to get that the Wronskian is equal to this. And so then we have our H's. We now have our H, okay, which is going to then go into this, and we combine it with our tesseract to get G, and with our G's, there's that goes into right here. So multiple step problem, obviously, but we have done it all, and so that is my G. That's my G. All right, people. So that is that. So where are we at with time? 1:48. Okay, so that's basically it. Dyads and Green's functions. This is the last page, and they spend 25 slides on this, but it doesn't really add all that much, if really anything. But it's sort of interesting reading. Dyads, sort of a mathematical structure that sort of fell out of use a lot, but is still involved in some things, in tensor calculations and some things. And very interesting is basically what you can do, an operation you can do with two vectors, like an inner product type of thing, but it results in a vector itself. So how do you create a mathematical operation that does that? Well, you do that with a dyad. So you do like an inner product thing, but the resultant is a vector. So that's what this last couple of pages tells you, shows you how to do. It shows you how to work with dyads. So basically tells you how to construct the three components of D from this operation, dyadic operation. But I'm not going to cover that because we're already at an hour and 15 minutes. Okay. All right. Take care, everybody. And this was the last lecture, actually, so that's good.